Welcome to this explainer. Today, we're skipping the basic definitions and diving straight into a real circuit design and problem-solving masterclass. We're going to be tracing logic, deriving equations, and building functional memory step by step. Let's get right into it. Here is our roadmap. 1. Combinational adders. 2. The memory blocks. 3. Excitation tables. 4. Sequential design. 5. Digital components.
Section 1. Combinational adders. Pure instant reaction.
Okay, let's start with a worked example of a half adder. Take a look at this truth table. Now, here is your first practice exercise. I want you to pause the explainer right now. Seriously, grab a pen and try to derive the Boolean expressions for the sum and the carry based entirely on this logic. Okay, let's see how you did.
And here is the solution. It's actually pretty elegant. An XOR gate maps perfectly to your sum equation since it only outputs a 1 when the inputs differ. And an AND gate, well, that captures your carry perfectly. But we have a major design limitation here, right? This circuit has 0 capacity for a carry-in bit. So, to solve that limitation, we scale up to the full adder. The construction methodology here breaks down into 3 simple steps. First, factor in that carry-in bit. Second, cascade 2 half adders together. And third, combine their carry outputs with an OR gate. Which brings us to the actual hardware. Let's do a quick mental trace right now. Try this out. If input A is 1, B is 0, and your carry-in is 1, trace those signals through the cascaded half adders. If you follow the logic paths, you'll find the final sum is 0 and the carry out is 1. Pretty cool, right?
Section 2. The memory blocks. Enter sequential logic. Now, since you already know the basic definitions, let's look at this purely as a design constraint. For our next set of problems, our hardware actually has to evaluate the previous state alongside the current inputs. We are literally introducing time and memory into the equation. Let's trace a sequence using the foundational SR latch. Imagine set and reset both jump to 1 simultaneously. If you trace that through those cross-coupled NAND gates, you'll see it completely breaks the complementary Q and Q' outputs. This is the infamous invalid state, and it's exactly what we need to engineer our way around. And to bypass that invalid state, engineers evolved the SR latch into what you see here, the D, JK, and T flip-flops. For our upcoming circuit design problems, you really need to commit these characteristic equations to memory. Pay special attention to the T flip-flop because it makes toggle behavior for counters so much simpler.
Section 3. Excitation tables. Time for some reverse engineering.
To actually design complex synchronous circuits, we rely heavily on excitation tables. We aren't just finding outputs from given inputs anymore. It's the exact opposite. We are working backward from a required state transition to figure out exactly what inputs we need to make that happen. It is the ultimate engineer's tool. Section 4. Sequential design. We're building a Mod 4 upcounter. Let's walk through a fully worked design for a 2-bit Mod 4 synchronous upcounter. Step 1. We always start by drawing the state diagram. This perfectly maps out our required loop, counting from 0, 0 all the way up to 1, 1, and then looping right back. Step 2 is creating the state table. Time for another practice exercise. Pause the explainer again, using the T flip-flop excitation rules we just talked about. Try to derive the required T1 and T0 inputs needed to force these exact state changes. Give it a shot yourself before we look at the answer. Okay, here is the solution for step 3. When you map your results into a K-map, you'll find that T0 simplifies down to a constant 1 because it's always toggling. T1, on the other hand, simply equals Q0. You'll want to lock this exact 4-step workflow in. Draw the diagram, construct the tables, simplify using K-maps, and then draw the circuit. This is the golden rule. It's the exact algorithm you're going to use to solve literally any sequential design problem they throw at you. And step 4 brings us the physical hardware payoff. Notice how scaling this up to a 4-bit synchronous counter means we have to tie each T input to the logical AND of the previous Q outputs. Trace the clock pulse here. Because it's a shared clock line, every single bit toggles at the exact same time. This brilliantly avoids the lag and propagation delay you get with older ripple counters. Section 5. Digital components. Standard IC blocks. You already know a multiplexer, or a MUX, acts like a switchboard to route inputs. But let's look at a much more advanced application, using it to implement arbitrary Boolean functions. By tying specific data lines high or low and using the select lines for your variables, you can actually realize complex logic without wiring up individual single logic gates. It's incredibly efficient.
We also need to integrate components like decoders, encoders, and registers. When you're tackling design problems, always remember to account for priority encoding, just in case multiple inputs hit your encoder at the exact same time. Oh, and make absolutely sure you are tracing those parallel load signals correctly on your registers.
Finally, let's look at the shift register. One last practice exercise for you. Imagine a binary sequence of 1011 arriving at the serial input. Try tracing that exact sequence through these flip-flops across 4 consecutive clock pulses. If you follow the data, you'll see exactly how this component perfectly executes serial to parallel data conversion.
So, you've now successfully traced and designed combinational adders, sequential memory, and standard digital ICs from scratch. But as we look ahead to full-scale system architecture, I want to leave you with this design challenge. How do we actually orchestrate all these individual components together into a central processing unit that executes real software code? Think on that like a giant puzzle, and we'll see you in the next explainer.